Alright, let's build a simple pendulum in your mind and break how it works step by step. Picture a string tied to a fixed point with a small heavy bob at the end. That's it. One pivot, one string, one mass. I pull the bob a little to the side and let it go. It swings back and forth in a smooth arc. What's actually happening? Gravity is pulling the bob straight down, but the string forces it to follow a curved path. When the bob is off to the side, gravity has a component that points back toward the bottom. That's the restoring force, the thing that tries to bring it home. At the highest points, the bob has maximum potential energy and almost zero speed. At the bottom, it has maximum speed and minimum potential energy. Energy keeps trading places, potential, kinetic, and back again. Now, the math that makes a pendulum awesome is surprisingly clean if the swing is small. For small angles, that restoring force is proportional to the angle. That makes the motion very close to simple harmonic motion. Translation: the swing is smooth and repeatable, and the timing barely changes. Here's the headline formula for the time of one full swing, called the period. T equals 2 pi times the square root of L over G. T is 2p Lg. L is the length from the pivot to the center of the bob. G is the acceleration due to gravity, about 9.8 meters per second squared on Earth. 3 big takeaways. 1. The period depends on length, not mass. A baseball, a bowling ball have the same timing. 1. Longer pendulum, longer period, double the length, and the period scales by the square root of 2. 1. Location matters because G changes slightly. On the moon with lower gravity, a pendulum swings slower. Quick example: if L is 1 meter, then T2P1 9.8, 2.01 seconds. That's about 1 second each way. Want a 2-second full period? Keep it around 1 meter. Want a 1 second full period? Shorten the length to about 12.25 meters because T scales with the square root of L. There are some fine print assumptions. Small angles, like under about 15 degrees, so that's in theta. A light, non-stretchy string and a rigid pivot. Minimal air resistance, go bigger angles or add drag and the timing shifts a bit. If you're curious about frequency, the number of swings per second, it's just F equals 1t. So a pendulum with t equals 2 seconds has F equals 0.5 hertz. Real world hacks to make a steadier timer: keep the swing small and the string light. Measure length from the pivot to the bob's center. A few centimeters matter. To adjust the period, slide the bob up or down to change L. And if you want to visualize forces at an angle theta, the tangential restoring force is roughly mg theta for small angles pointing toward the bottom. That's the engine of the oscillation. So that's the simple pendulum: a string, a mass, gravity, and a clock hiding in plain sight. Next time you see one, you'll know exactly why it keeps such steady time and how to tune it with just a tape measure.